context of Elixir and think about the general ideas that apply to typing dynamic languages in general. So I'll try to abstract those ideas. The agenda is that I'll pinpoint a few main design or technical issues that can arise when doing that. I'll highlight the strength of using set-theoretic types to solve them, and I'll give a little crash course on implementation, because if I'm presenting a solution, it would be good to have a plan towards that. So, retrofitting types onto a language that is already being used is challenging. One reason, you have to match the programmer's expectations. They already know the language, and it would be very bad. Well, it would be bad, for instance, if the type checker you're trying to give them is not able to type check a program that they know is correct, or if they had to modify the code for it to type check. There's also potential for clunkiness. By that I mean giving extra work to the programmers, having a type syntax that is overbearing, that gives you more safety within your program, but that does not necessarily give you more information about what it does. And to go further into the specifics, I've thought about three different ways, three different issues in that area. One has been defining a syntax for types before defining their semantics. And I chose Python to illustrate that. Type annotations, their syntax was introduced in 2006, actually, way before there was any way to type check them. And I would say it's not really clunky. You annotate the argument and the return type. And when you look at that, I think there are many questions that you want an answer to. Like, is the language going to ensure that I only apply this function to strings? And does this mean that if I give a string to my function, I get a string? And the answer is none of that, because by default, Python doesn't do anything. It doesn't look at those annotations. You have to pass them to an external type checker. So the fact that this is a different thing that programmers have to work with means that there's a bit of an awkward situation. Awkward enough that last year there was a typing council created to guide the integration of types into Python. Actually, Elixir Along is similar. We have type specs, and they are reasonably nice to read. But they have to be passed to an external tool to have any say, any opinion on your program. And even more, the typing discipline that is used to check those annotations is a static analysis that uses success typings. Success typings, they are an over-approximation of the type of your arguments. It's going to give the type of all the values for which it doesn't fail, and it's an over-approximation of the return type of your function. It's going to give you all of the types that the function may return. And it runs a bit counter to the usual intuition that programmers want, which is that if this function is given some input, then it will give this input back. And in both cases, because we are using, in the case of Python, gradual typing, the type checker is not going to be able to guarantee you that you're never going to use this greet function in Python with only strings, because you have something which is the dynamic type that is going around, and that which types values that you don't know anything about. And so the possibilities of safety are more difficult to attain. The reason why semantics for types, why this syntax was introduced, I'm not saying it's really a bad decision, but I think that there was a problem in the first place of expressivity, which is that it is hard to produce types that match the semantics of dynamic languages. And common idioms, like this little Python function, have a type that varies on its input. So this function, if x is a list, it's going to build a list comprehension and apply it recursively to the elements of the list, and otherwise it's going to output an integer. So reasonably, you would annotate this function like that, saying, I want to apply this to list of integers, and I want to return a list of integers or integers. And this is a union type that can be written in Python. But this doesn't pass the type checking because the type checker sees that fooify applied to x may be a list of integers within your list comprehension. So you're not able to type check this. And the reason might be that it was decided that you would write type annotations like that, but the truth is that you need something more. You need something more precise. So you can do that by using some overloading. So import overloading, and then you write additional type annotations that correspond to each case, to each way you want to use your function. So the first one is from integers to integers, and the second from lists of integers to lists of integers. And now we have, it really looks like some additional thing to understand, because you have to know what type is being used when my function is being called. And the answer is that it's the overloadings that are going to be used, so either int to int or list to list, which is unfortunate, because now the other type, the one that uses unions, it can be used. So if you wanted to abstract your function, fooify, and create another function that's just going to apply fooify to some argument that might be an integer or list of integers. So callable here, it represents just a function type from ints or integers or lists of integers to integers or list of integers. And while this program works, the type checker refuses it. So the solution I propose you is to have a type that captures this behavior. The fact that you have a list of, you have a function here written in Elixir that has both behaviors. It has two function types, and this is an intersection here, and it has the type of functions that when given list of integers, they return list of integers, and when given integers, they return integers. And you can now type check this function without modifying the code. By that I mean importing some overloading operator, writing all those annotations, and more importantly, it fits into a single type annotation. And there's something about the cognitive load that Simon was talking about that speaks to me there, because I think it's important that types, they capture both the intuition of the programmer about their program, and they also give information to someone that's just coming across some random code. And on top of that, because we're using a richer foundation to express the types, we have now subtyping polymorphism for free. Because this type, this intersection of two types, it is a subtype of the more general type. You see, if you have a function that, when given list of integers, returns list of integers, and when given integers, it returns integers, it's true that if you give it one or the other, it's going to return one or the other. And having this decidable subtyping relation is part of the framework of set-theoretic types that we're using. There's a third source of complexity in typing dynamic languages is, I think it's gradual typing. So gradual typing is a good approach to making possible the transition from untyped code base to typed code base. It also provides an escape hatch for dynamic languages. I think the idea is that some features are inherently dynamic, so or either that or it's still difficult to type check them. So it's interesting to have a dynamic type that explicitly can serve as an escape hatch for your program. The issue, though, is that you're integrating a new type in your foundation, and it has to play well with the usual typing rules that you normally write. There's also a possible issue with programmers is that they're going to be, how could I say, surprised at the behavior of the dynamic type because it's going to interact throughout the program in different ways because it has to be checked sometimes, because sometimes it can relax the safety of the program without them noticing. And also, its handling really depends on which choices have been made in the language that they're using. For example, let's see in TypeScript, they have two dynamic types. One is called any, and the other is unknown. They both represent values whose type is unknown, so which could be anything at runtime. The difference is how they interact with the meta theory. Any is going to go through a program without ringing any bells, and the type checker is not going to try to tame it in a way. While unknown will only be able to be used behind an explicit type check. So this introduces for the programmer a difficulty that they have to think both about the semantics of their code, but also about the rules, the rules of the meta theory around the type checker. And I think we can always be simpler. I'll just show how I think we can integrate the fact that we have dynamic in a type system and the fact that we have some static type information when writing code, how we can both mix both of those two into the type representation, into dynamic. So when you're type checking some code in a dynamic language, in dynamic mode, you're interested, for instance, in Elixir here, in knowing what type of values this function is going to output. And here, we know that this function is going to output integers or booleans. But because we are in dynamic mode, if we were trying to enforce type safety over just this knowledge, we would make this code that is not annotated fail. So, and we would do that without having the programmer, having told us that they want subtract to be possibly applied to integers or booleans. So it's a little bit unfortunate because we have some static information here, and if we use it, we are giving bugs that possibly uses do not want, because we here are doing a gradual typing for language. Instead, what we can do is to say that this function outputs an intersection type, the intersection of dynamic, with the union type integer or boolean. What this means is that this can be any subtype of integer or boolean, and this type is going to interact with the typing rules of your system in a more relaxed way in this case, because it sees that when you do a plus negate of b, dynamic and integer or boolean can become an integer at runtime. So in a more relaxed typing discipline, this function type checks. However, because you've retained the static type information within the type, you can find type errors when you try to do the same, but with the list concatenation. And you see here that you have incompatible types. So I am not presenting things that are impossible to do in the realm of type systems. I just want to show how some problems that imply sometimes clunkiness in writing types, and sometimes some extra meta theory that programmers have to think about, they can be solved by using a foundation of set-theoretic types. And instead of extra meta rules, you have type operations on your types. So subtype polymorphism and ad hoc polymorphism that we saw in the first place with the intersection of function types. One additional example is if you have pattern matching, you can check that this pattern matching is exhaustive by looking at the type of the coming values. So if E has type T, by looking at the type that each pattern captures, T1, T2, T3, and checking that this type T is a subtype of the union of all the types captured by all those patterns. And this is just an operation on your types. Similarly, you can check whether a branch is unused. For example, the second branch, by checking the type that you obtain if you take the values that come in, if you retract the values that are matched by the first pattern of type T1, and if you intersect with the possible values matched by pattern 2. And here I'm using and not to denote type difference, whose intuitive meaning is that T1 and not T2 is the type of values that are of type T1 and not of type T2, literally doing set operations there. You can also use your types to encode type refinements that you do, even on top of dynamic. So if you do checks on your expressions, you know that the static information that you give them is going to be retained in order to type check the rest of your program. There are issues with set-theoretic types. The first one is that you lose the property of having the most general type, a notion of most general type that you can infer. So inference now becomes more about finding the most precise type that you can for your program. And if it is good enough, it is good enough. But in any case, this property that exists in a statically typed language is perhaps too strong for dynamic ones. They're also a bit hard to implement because, well, it's an extra complexity. You have to have a data structure and implement set operations on top of them. And actually, I'll show a bit how you can do that. So what we need, we're going to take a key value data structure where each field contains one of the distinct types that you want to represent. So if you have integers, floats, atoms, each of those is going to have its specific field. And it's important because for them to be distinct, because your general type is going to be the union of each field. And on this data structure, you need to implement intersection, union, difference, the end not, and subtyping. So, I've started putting a little bit of boilerplate there. I've defined the top type of all my types. It is term. And it says that it contains integers, it contains floats, it contains atoms. Oh, yeah. We're starting with just those three base types. Integer, float, and atoms. I've defined also the bottom type of them, and it is a type that contains none of them. So I can define all of my base types like that. The integer type contains integers, does not contain floats, and neither it does atoms. We can define floats. They contain floats. And they don't contain atoms. And finally, atoms. So what we're going to have in this first place is just a set of base types. And on top of them, we're going to start implementing the set operations. So if I want to do the union, the union of two types is going to look at each field and see if one or the other is present. And if none, then your type is not present at all. So it can be done by just a map merge on two types. And since we've put booleans in all types, we just use a boolean operator. The intersection is going to do exactly the same, but with and maybe I can speed this up a little bit by copy-pasting here. There's the... Thank you. So now we have our three set operations defined. Union, intersection, and for difference, I just put and not, because, for instance, if I want to compute number and not integer, I'm going to obtain float, and the way I do that is saying that in number there is the field, the boolean true for float, and it's not an integer. So now that we have some set operations, we can do a bit of checking. So, yeah. I can define some custom types on top of those. So number, it's going to be the union of integers and floats. And I can check that this difference does work. I can now do any type of set operations on my types. So if I want to see that the intersection of integers and floats is empty, I can do just that. Let me define. If I want to see that the union of the type with anything is the top type, I can do that as well, etc. So now that we have base types, we may want to add something a little bit more precise. And for instance, we can do singleton atoms. So if we want to have singleton atoms, we're going to have one atom, one singleton. Because we have unions, we need to have the union of a few of them. We need to have the top type for atoms, so it's going to be atom as well. And because we have difference, we need to support as well difference of the set of all atoms minus a few atoms. So saying that, it's possible to see here that we only need two forms to represent all the possible representable atoms, atom types. So those two forms are just a union of a few atoms, and we're going to use a set to represent a few atoms, or a negation of a few atoms. And the way we're going to add that to the language, so first I'm going to define what's going to be the top type that represents the whole set of atoms. So it's going to be, the top type is what happens if I have not retracted any type from any atom from my top type. So this is atom minus nothing. And the bottom type that represents no atom is going to be a union of an empty set of atoms. Actually, yep. And now I can update my representation. So atom 2 here is going to become atom top. So I'm changing the booleans to this representation. And I've got to change them around here as well. All right, so now I have the top atom type, which is here, and I can define some function that creates me a union of a few atoms. So when this is a list, all right. Now, what we have to do, because we've added a new type, we have to update the intersection, union, and difference functions. And to do that, we have to define the union of two of those atom types. And it's going to be fairly easy. So if we have a pair of representations for our atoms, we do a disjunction of cases. If those are two unions, so if what we're doing is the union of two unions of types, we're going to use just a map set union, because there's nothing much going on. So doing the union here is just about calling map set union of those two. If we have a negation and a union, what that means is that we have the set of all atoms minus a few ones, union, a set of a few atoms. So what we have at the end is the set of all atoms minus a few ones minus the few atoms that we added back. So what we have is still a negation, but now we have to subtract the atoms that we add to the ones that were subtracted from the whole set of atoms. So it's going to be the difference of set 1 with set 2. Every case is like that, just a bit of a disjunction on the different cases. And I'll copy paste the rest of them. And now what I just have to do is to batch up my intersection, union, and difference function with this new case. So adding the case where we have to handle atoms. And now we can look at them. So, for instance, the intersection of, well, just if we have the atoms, okay, an error, and the atoms, okay, and something R, we can see that this is just going to be the atom, okay. As you see, all that we need when we want to add a new data type is to add a new field to the desker. So if we want more structured types, for instance, maps, tuples, lists, they each get a new field. There's going to be, the issue for those more complex types is going to be about normalization for printing, but it's something that you can do through heuristics. You also have to find a correct mathematical representation for each of them, but once you've done it, it's done. You just implement the logic once, and it's done. And wait. And I will show this. And finally, about dynamic, it can also be implemented as an extra field on this descriptive representation, and it's going to be handled the same as with all the rest, with intersections, unions, and subtyping check. So, in summary of this talk, set-theoretic types, they allow you to solve some general issues. Some general issues from typing dynamic languages by shifting away the complexity from the typing rules to another complex task that I showed you a little bit about. The set-theoretic types, they can also be implemented à la carte, meaning that you start with base types and then you add the exact precision that you want. You don't have to be as precise as you want from the start, especially if you have a dynamic type that's going to be able to help you represent things for which you need the type checker to be more relaxed. Thank you, this was great. And any questions?
Okay, so round of applause. Guillaume. Yes, and we do have some time for questions.
Hi. Yeah, thank you for a very nice talk. So I have a quick question. So far you seem to operate on concrete sets of types, which assumes that you know all the types up front. So my first question is, what happens if you want to start working with types that you might not see beforehand, like with some kind of abstract types? Do you need to go through dynamic, or is there some structured way to deal with those types? And secondly, you've already showed some subset types when you've been discussing subsets of atoms. What happens if you lift those operations to other types and you start talking about subsets of functions or subsets of constructors like lists over a certain type or lists over a certain type which satisfies a predicate?
So your first question, I'm not sure I understood it. It was, what if I need to work with some data type that I've not implemented yet? Well, there would be, I think the easiest way would be to add a base type for that specific data type. So you know this base type exists, and you can assign it to any occurrence of that structure. And then, if you needed more precision within that within that structure, to actually type check your programs, you could intersect it with dynamic, which would tell your type checker that this can be any subtype of this huge base type, and that would be a first step. Of course, there would be some imprecision in it, and you would not capture errors that are related to that structure, but for some of those, it can be difficult. Your second question about functions, you can have functions and you cannot have a specific function type within this descriptor. Yes, it works, and it gives you unions, all possible unions and intersections of single arrows from one type to the other. So that supports what I showed earlier, the intersection with the end. About constructors, I've not worked on that specifically, but I think it can just be done in the same way that we handle singletons. This pattern for implementing singletons, it's about realizing that something can be either finite, you have a union of a few of those things, or infinite, that is all the possible things minus a few ones. And this can be used to implement other specific structures like that.
Okay, more questions? So you had that Python example at the beginning where, like, if it's a number, it's multiplied by 2. If it's a list, we recurse on each element. So that's, not something you can type with this. But you could if you had like limit types or fixed points. And so my question is there any like complication with those that, like why are they not added, given that even your first example showed something that would require them? Is there something very tricky once you add them to this same approach?
Is there something what, sorry?
Like, is there something tricky? Like, does something go wrong? There's something becomes really hard if you add them to this approach?
I don't think there's anything really tricky there. I think that maybe even Python could even do some sort of refinement of the type after the type check and realize that this function could work.
No. So my question is the following. So you have this Python program without any type annotations, right? And its type is not the type that you can write here. Its type could be, like, it's a limit type of either int or, like, it's a limit of in t of int or list of t, right? Yeah. Because it can go arbitrarily deep.
It can have a, that's good question. So I assume that writing an annotation here means that you don't want the full generality of this function. And I have no idea actually what would be the, well, yeah, with set-theoretic types you could do something like that, define a recursive type that's sort of a tree with ints inside, and this function is going to do that. That's fairly complex and really not the point, but yeah, with some recursive types I think you could write a one-liner annotation with set-theoretic types to have the most general one. Probably.
Yeah, so I mean, that's not the question. The question is, yes, of course you could do that. My question is, did you not add recursive types or limits or fixed points because they would break? Like, is there something that goes wrong, or is it just like not added because, I don't know, you thought that they're not really useful or not needed to get something that's good enough? Or?
You're asking about the Python type checker or our approach? Because
okay, I guess my question is that, like, your approach, the one that you're presenting, right? Like, you have subtraction, you have unions, you have intersections, but you don't have, or at least haven't shown us limits or fixed points.
We have recursive
You do? Oh,
types.
you just haven't showed us.
Yes,
like,
no, I didn't talk about it.
Okay,
We have we support recursive types, polymorphism, with a local type instantiation, but yeah, that's a lot of things to talk about.
More questions?
Thank you. This looks very elegant. I think it's been about 30 years worth of research into looking at type errors for type systems, and I wondered, is this something that you've had to focus on, and have you any insights on how you give good type errors when things go wrong? You know, there's a history of PhD theses on trying to explain type errors in appropriate ways, all of which have said some useful things, but it is, you know, it's a challenging problem, and I wondered what insights you get from this this approach. So
you're asking what about type errors when we go this road? I think there's one advantage and one drawback to this approach. Mm-hmm. I'll go with the advantage first. Okay. It's that now when you do type errors, you always have a type that has retained the full semantic information about what has happened to an expression. So you can grab this type and make it say whatever you want, and you can try to print it as best as you can. And that can give some real precision. For instance, for when you do pattern matching, here the way we check exhaustivity, it's by computing a type. So that means that if you don't have exhaustivity, we have computed the type that is T minus all the type matched by the patterns, and we can print it. We can say this is the type of the values that you don't match. The drawback is that you are retaining all the information. So maybe it's not what the programmer wants to see, and it's a bit too complex. So for that, there are heuristics. One of them is if the programmer has written type annotations, you use them to like prettify your type using the information that they gave you, like using custom data types. There's one heuristic I like, is that you can do transformations on set-theoretic types. For example, you could do double negation. It's going to give you the same type. So possibly you could try to do that and print the one that's print the shorter type. There's a lot that can be done.
Okay, we are out of time. Let's give a warm round of applause to Guillaume.